In this lecture, we will introduce some basic sorting algorithms.
We're now going to take a look at several algorithms that involve sorting a list of elements. For our purposes, we're going to be looking how to sort an array of elements. We could do this for linked lists, but we're just going to talk about with arrays. And to make matters as simple as possible, we're going to assume that the arrays have integers. We can easily apply this to arrays of doubles, characters, objects, and so forth. And we're also going to assume that all this sorting can be done inside our main memory. It is possible to do sorting on a disk, and that's called external sorting, and we will be talking about a couple of strategies for that later on. What we're going to see here is that we'll discuss some very simple sorting algorithms, and each of these algorithms takes O of n squared time. Now, I will say something up front. N squared time is a horrible running time for a sorting algorithm. If you were to implement any of these algorithms in an actual job setting, you're probably going to get laughed at or fired or laughed at and fired. But the reason why we go over these algorithms is because they are very simple to understand, and it's a great way to introduce sorting. We will take a look at some more complicated algorithms that do take O of n log n. Now, it would be nice to have linear time algorithms, and there are some special cases where we can do that, but in fact, for any general purpose sorting algorithm, it's going to require omega of n log n comparisons. So we're never going to get a linear time algorithm for sorting in general, but we can get some improvements in very special circumstances. Now, for the algorithms we're going to be talking about, we will assume that each of these algorithms has an array of n elements, and each element in the array does have something. If elements are missing some values, that could make things a little tricky. So we're going to assume that we're passing a full array of values. And all these algorithms that we're going to be discussing use what we call comparison-based sorting. And what that means is we're going to be comparing two elements in our array, and then whenever we need to, we're going to swap the two values. So we're going to put them in different spots, but we're going to swap them. We'll start by discussing the bubble sort algorithm. One of the simplest sorting algorithms out there is called bubble sort. Here's the idea. We start by comparing the first two elements in our list. So let's say it's A0 and A1. We put the smaller value in A0, we put the larger value in A1. And then we're going to repeat this for each pair of consecutive elements. So then we're going to compare A1 and A2, put the smaller one in A1, put the larger one in A2. We then compare A2 and A3, put the larger one in A3, and we do this all the way up to AN minus 2 and AN minus 1. What would happen after this one pass, the largest value in the entire list should be in AN minus 1. So then we're going to repeat this whole sweep again, going up to AN minus 2. So we would put the smaller one on the left element, we put the larger one on the right element, and we keep going up to AN minus 2. That means at this point, AN minus 2 has the second largest value. We'll do it again, and on the third iteration, AN minus 3 should have the third largest value. So we will do this n minus 1 times. And what that means is after we do n minus 1 iterations, the entire array will be sorted. Let's do an example of bubble sort. So let's say our list is 34, 8, 64, 51, 32, and 21. We compare positions 0 and 1, so we're going to put the 8 in A0, we're going to put the 34 in A1. We'll then compare positions 1 and 2, so they don't really change because 31 is smaller than 64, so it remains unchanged. We'll then compare positions 2 and 3. Since 51 is smaller than 64, we're going to put 51 in A2 and put 64 in A3. We then compare positions 3 and 4. 32 is smaller than 64, so we put 32 in A3 and 64 in A4. And then we compare positions 4 and 5. 21 is smaller than 64, so we're going to put 21 in A4, and 64 is going to be in A5. And notice at this point, the largest value, which is 64, is in A5. So what we saw in that last example is after one pass, the largest value should now be on the far right side of our list or our array. So the observation here is with each iteration, the largest values will bubble up to the right side of the array. That's why it's called bubble sort, because the largest values will keep bubbling to the right side of the list. Let's now go back to our example and we'll do the second pass of the algorithm. So we're going to compare positions 0 and 1. 8 is still less than 34, so we don't swap anything. We'll compare positions 1 and 2. 34 is less than 51, so we don't do any swapping here. We'll then compare positions 2 and 3. In this case, 32 is less than 51, so we will swap the positions, or swap the values. So 51 is now at position 3, and 32 is at position 2. And then we'll compare positions 3 and 4. So since 21 is less than 51, 21 is going to be at position 3, and 51 is going to be at position 4. So now here, A4 has the second largest value at this point, which is 51. We'll now go to our third pass. So we're going to compare positions 0 and 1 again. 8 is still less than 34, so we don't make any changes. We'll then compare positions 1 and 2. 32 is less than 34, so we're going to put 32 in A1 and 34 in A2. And then we'll compare positions 2 and 3. 21 is less than 34, so we're going to put 21 in A2, and we're going to put 34 in A3, and that completes our third pass. We'll then compare positions 1 and 2. 21 is less than 32, so we're going to put 21 in A1 and 32 in A2. And then we don't need to do any more comparisons because 32 now has the fourth largest item, which is stored in A2. We'll then do the final pass, which is really we just compare positions 0 and 1. 8 is less than 21, so we don't do any swapping, and that completes our algorithm. Here is our bubble sort code. So we see that we have two nested for loops, which gives you an idea of why this is going to be an O of n squared time algorithm. The outer for loop is going to take care of the number of iterations. And notice that we start with n minus 1, and then we go backwards. And that's because in the inner for loop, our comparison here is if I is less than j, right here. So the first time we go through the algorithm, we're going to have I go up to n minus 1, or at least one less from that. And then the next iteration, we're going to have I go up to n minus 2, and then n minus 3. So this helps us with determining the stopping point for any particular pass in our algorithm. And then inside the body of this loop, we're comparing AI with AI plus 1. And if we need to make a swap, we'll do so. Well, how do we swap? Well, that's taken care of right here. So to swap two values, we need to have a temporary variable to store one of the values. I think we mentioned before in CS121, but just as a reminder, we have to have an extra variable because if we just try to swap the values without it, we're going to override one of them. So we'll store AI in a temp, and then we can store AI plus 1 in AI, and then we can take what's in temp, which was AI, and store it into AI plus 1. To show that bubble sort does take O of n squared time, let's actually look at the total number of comparisons being made. So the first iteration, we're going to have n minus 1 comparisons. The next round, we're going to have n minus 2 comparisons, and then n minus 3 all the way to 1 comparison for the last iteration. Well, what does this sum come out to be? Because we can just add up all these comparisons. Well, this turns out to be the sum of I, where I goes from 1 to n minus 1. Well, what does that turn out to be? That's n minus 1 times n minus 2 all over 2, which is approximately n squared over 2. And since we do ignore constants in our O notation, this takes O of n squared time. And this does make sense because as we saw in the code, we have O of n iterations for the outer for loop, and then each iteration of that loop takes O of n time because we're going to be comparing and swapping the values in the inner for loop.